Hey there, science fans! Have you ever felt the ground shake beneath your feet, like a giant was playing a game of marbles with our planet? That, my friends, is the incredible power of an earthquake. Earthquakes are like shockwaves that ripple through the earth. They shake things up, literally. Imagine a sudden release of energy, kind of like popping the cork off a bottle of champagne, but on a much larger scale. This energy travels as waves, making the ground vibrate and sometimes even split apart. These tremors can be as gentle as a whisper or as powerful as a freight train, causing everything from mild shaking to widespread destruction. But what causes these earth-shattering events? Well, to understand that, we need to take a peek beneath the surface of our planet. Get ready because things are about to get interesting. Now, some earthquakes are more memorable than others, leaving a lasting impact on our planet and its people. Take the 2011 Tohoku earthquake in Japan, for example. This massive earthquake, registering a whopping 9.0 on the Richter scale, unleashed a devastating tsunami that caused widespread damage and loss of life. Another unforgettable event was the 2010 Haiti earthquake. This catastrophic quake, measuring a powerful 7.0, struck near the capital city of Port-au-Prince, causing immense devastation and loss. These events serve as stark reminders of the sheer power of earthquakes and the importance of understanding these natural phenomena. They highlight the need for better preparedness, early warning systems, and resilient infrastructure to mitigate the risks associated with these powerful events. So what's going on beneath our feet that causes these seismic shenanigans? Well, picture this. The Earth's outer layer, called the lithosphere, isn't one big, solid piece. It's more like a giant jigsaw puzzle, made up of massive plates called tectonic plates. These plates are constantly on the move, shifting and sliding against each other, albeit very slowly. Think of it like a slow-motion dance party happening beneath our feet. But sometimes these plates get stuck and stress builds up, like a tightly wound spring. When the pressure becomes too much, the plates suddenly slip and release a burst of energy. And boom, that's an earthquake. We're going to explore these tectonic plates, the fault lines they create, and the incredible science behind these earth-shaking events in more detail. So buckle up, science fans! Okay, science explorers, let's dive deeper into the Earth's surface and unravel the mystery of these moving plates. As we learned, the Earth's outer layer, called the lithosphere, is broken into these massive pieces called tectonic plates. These plates aren't just chilling, they're constantly on the move, floating on a layer of hot, molten rock called the asthenosphere. Imagine a pot of simmering soup, with croutons representing the tectonic plates. The heat from the stove, the Earth's core, causes the soup, the asthenosphere, to bubble and move, carrying those croutons along for the ride. That's kind of what's happening with the tectonic plates. Now these plates move at a snail's pace, about as fast as your fingernails grow. But even at this slow speed, their interactions create incredible forces that shape our planet. It's like a slow-motion ballet, but instead of graceful dancers, we have massive chunks of Earth's crust bumping and grinding against each other. Now things get really exciting and shaky when these tectonic plates collide. Imagine two bulldozers pushing head-on. That's the kind of intense pressure that builds up at these convergent plate boundaries. The immense force generated can cause the plates to buckle, fold, or even fracture. These collisions are the most common culprits behind those earth-shattering earthquakes we've been talking about. And guess what? These mighty collisions are also responsible for creating some of Earth's most magnificent features, majestic mountain ranges. The Himalayas, for example, were formed over millions of years as the Indian plate collided with the Eurasian plate. Talk about a powerful slow dance. But convergent plate boundaries aren't the only places where earthquakes strike. Let's explore what happens when plates decide to part ways. Hold on tight, science fans, because sometimes our tectonic plates like to play tug-of-war. At divergent plate boundaries, instead of colliding, the plates move apart from each other. Imagine two friends pulling on opposite ends of a pizza. More pizza for everyone, right? Well, in this case, it's molten rock from the Earth's mantle that rises up to fill the gap, creating new crust. This process is called seafloor spreading and is responsible for the ever-growing mid-ocean ridges that snake around our planet like underwater mountain ranges. But just like breakups can be messy, so can divergent plate boundaries. As the plates pull apart, they can create cracks called rifts, which can trigger earthquakes. While these earthquakes are typically less intense than those at convergent boundaries, they're still a reminder that our planet is a dynamic and ever-changing place. Now, imagine two tectonic plates sliding past each other horizontally, like two ships passing in the night. This is what happens at transform plate boundaries. While they might not be creating mountains or new crust, these boundaries are notorious for generating some of the most powerful and destructive earthquakes on Earth. The most famous example of a transform plate boundary is the San Andreas Fault, which stretches for hundreds of miles along the coast of California. The Pacific Plate and the North American Plate grind against each other along this fault, causing frequent earthquakes as stress builds up and is suddenly released. These earthquakes can be quite strong, shaking things up in California and reminding everyone of the immense power hidden beneath our feet. So, whether plates are colliding, pulling apart, or sliding past each other, one thing is clear. The Earth's tectonic plates are in constant motion, shaping and reshaping our planet and occasionally giving us a good shake. Okay, science sleuths, we've been talking about tectonic plates moving and grooving, but what happens when they bump and grind against each other? That's where fault lines come into play. Think of fault lines as giant cracks or fractures in the Earth's crust, where these massive plates meet and interact. They're like the battle scars of our planet's tectonic dance-off. These fault lines aren't just random cracks. They come in different flavors, each with its own unique personality and earthquake-generating potential. We're going to explore three main types of faults: normal faults, reverse faults, and strike-slip faults. Each type tells a different story about the forces at play within the Earth's crust. Understanding these fault lines helps scientists study past earthquakes, monitor current seismic activity, and even make predictions about future Earth-shaking events. So, let's grab our geological magnifying glasses and get up close and personal with these fascinating features. First up, let's talk about normal faults. These faults occur when tectonic plates decide to give each other some space. Imagine two friends pulling a wishbone apart. That's the kind of pulling force, called tension, that creates normal faults. As the plates move apart, the crust stretches and thins, eventually cracking under the pressure. The block of rock above the fault, called the hanging wall, slides downward relative to the block below, called the footwall. It's like sliding down a playground slide, but on a much grander scale. Normal faults are often found at divergent plate boundaries, where plates are spreading apart, like at the Mid-Atlantic Ridge. They can also occur in areas where the Earth's crust is being stretched or pulled apart. Now, let's talk about reverse faults, where the opposite happens. Instead of pulling apart, these faults form when tectonic plates decide to get up close and personal. Imagine two sumo wrestlers pushing against each other. That's the kind of compressive force that creates reverse faults. As the plates collide, the crust is squeezed and shortened, causing the hanging wall to move upward relative to the footwall. It's like stacking books on a shelf. The higher you stack, the greater the pressure. Reverse faults are often found at convergent plate boundaries, where plates are colliding head-on, like at the Himalayas. These faults can generate some of the most powerful earthquakes, as the immense pressure from colliding plates is suddenly released. Last but not least, we have strike-slip faults where plates decide to do the sideways shuffle. These faults form when tectonic plates slide horizontally past each other, like two ships passing in the night. The movement along a strike-slip fault can be either left lateral or right lateral, depending on the direction of relative motion. Imagine standing on one side of the fault and watching the other side move. If it moves to the left, it's a left lateral strike-slip fault, and if it moves to the right, it's a right lateral strike-slip fault. The San Andreas Fault in California, which we met earlier, is a prime example of a right lateral strike-slip fault. As the Pacific Plate slides past the North American Plate, it generates frequent earthquakes, making California a hotbed for seismic activity. So there you have it, 3 types of fault lines, each with its own unique way of shaking things up. Hold on to your hats, science fans, because things are about to get wavy. When an earthquake strikes, it releases a burst of energy that travels through the earth in the form of seismic waves. These waves are like ripples in a pond, spreading out from the earthquake's epicenter, the point on the Earth's surface directly above where the earthquake originated. Imagine dropping a pebble into a calm pond. You see those ripples spreading outward, right? That's what seismic waves do. But instead of water, they travel through the Earth's rocky layers. And just like those pond ripples, seismic waves come in different shapes and sizes. We're going to explore the 3 main types: P waves, S waves, and surface waves. Each type travels at a different speed and has a unique way of shaking things up. By studying these seismic waves, scientists can learn a lot about earthquakes, like their location, magnitude, and even the structure of the Earth's interior. So let's ride these waves and uncover the secrets they hold. First up, we have P waves, the speed demons of the seismic world. P waves, short for primary waves, are the fastest type of seismic wave, traveling at speeds of up to 14,000 miles per hour. That's like traveling from New York to Los Angeles in about 15 minutes. These waves are also known as compressional waves because they cause the ground to compress and expand along their direction of travel. Think of a slinky being pushed and pulled. That's the kind of motion that P waves create. P waves are the first to arrive at a seismograph, an instrument that measures ground motion, after an earthquake. They can travel through solids, liquids, and gases, which means they can travel through the Earth's core and provide valuable information about the Earth's deep interior. Next, we have S waves, the ground shakers. S waves, short for secondary waves, are slower than P waves, traveling at speeds of up to 8,000 miles per hour. They're also known as shear waves because they cause the ground to move back and forth perpendicular to their direction of travel. Imagine shaking a rope up and down. That's the kind of motion that S waves create. Unlike P waves, S waves can only travel through solids, not liquids. This means they can't travel through the Earth's outer core, which is liquid. This characteristic of S waves provided crucial evidence that the Earth's outer core is indeed liquid. S waves arrive at a seismograph after P waves and cause more significant shaking, often responsible for the most damage during an earthquake. So, while they're not as fast as P waves, they're definitely the ones to watch out for. Last but not least, we have surface waves, the rolling thunder of the earthquake world. These waves travel along the Earth's surface, much like waves on the ocean. They are the slowest of the 3 types of seismic waves, but often cause the most damage due to their larger amplitudes and rolling motion. There are 2 main types of surface waves: love waves and Rayleigh waves. Love waves cause the ground to move side to side, perpendicular to the direction the wave is traveling, while Rayleigh waves cause the ground to move in a rolling motion, like ocean waves. Surface waves are what people often feel most strongly during an earthquake. They are responsible for the ground shaking that can topple buildings and cause other types of damage. These waves, while destructive, are also a reminder of the immense power of nature and the importance of understanding and respecting the forces at play beneath our feet. Now, science fans, wouldn't it be amazing if we could predict earthquakes with the same accuracy as we predict the weather? Imagine knowing exactly when and where an earthquake will strike, giving people time to prepare and potentially saving countless lives. While we haven't quite cracked the code of earthquake prediction, scientists are hard at work, trying to unravel the mysteries of these earth-shaking events. You see, earthquakes are incredibly complex phenomena, influenced by a myriad of factors deep beneath the Earth's surface. It's like trying to predict when a popcorn kernel will pop. You know it's going to happen, but pinpointing the exact moment is tricky. However, don't lose hope just yet. While precise earthquake prediction remains a challenge, scientists have made significant strides in understanding the patterns and processes that lead to these events. By studying fault lines, monitoring seismic activity, and analyzing historical data, scientists are getting closer to developing reliable methods for earthquake forecasting. Section 2. Early warning systems, giving time to prepare. While we may not be able to predict earthquakes with perfect precision just yet, scientists have developed early warning systems that can provide crucial seconds or even minutes of notice before the ground starts shaking. These systems work by detecting the initial P waves of an earthquake, which travel faster than the more destructive S waves and surface waves. Think of it like a relay race. The P waves are the speedy runners that alert everyone about the approaching S waves and surface waves, giving them a head start to prepare. These early warnings, even if just a few seconds, can make a world of difference. Automated systems can trigger alarms, stop trains, shut down gas lines, and even open elevator doors at the nearest floor, reducing the risk of injury and damage. Every second counts when it comes to earthquakes, and early warning systems are proving to be invaluable tools in mitigating their impact. Section 3. Technological advancements. Listening to Earth's whispers. Science never stands still, and the field of earthquake prediction is no exception. Researchers are continuously developing and refining technologies to better understand and monitor our planet's seismic activity. Sophisticated sensor networks are being deployed along fault lines, acting like sensitive stethoscopes listening to the Earth's heartbeat for any signs of trouble. These sensors can detect even the slightest tremors and transmit data in real time to research centers, providing valuable insights into the behavior of fault zones. Supercomputers are crunching massive amounts of data, running complex simulations to model earthquake scenarios and identify potential precursors to these events. By combining cutting-edge technology with a deep understanding of Earth's intricate processes, scientists are getting closer to unlocking the secrets of earthquake prediction. While the dream of precise earthquake prediction remains a work in progress, the quest itself is filled with hope and the promise of a safer future. Challenges abound, from the sheer complexity of earthquake processes to the vastness and inaccessibility of the Earth's interior. It's like trying to solve a giant underground puzzle with only a few pieces visible. However, the dedication and ingenuity of scientists around the world fuel the pursuit of this life-saving goal. As our understanding of earthquakes deepens and our technological capabilities advance, the possibility of one day predicting these events with greater accuracy becomes more attainable. Until then, continued research, advancements in early warning systems, and proactive measures to improve building codes and community preparedness remain our best defenses against the power of earthquakes. Well, science explorers, we've journeyed deep into the heart of our planet and uncovered the fascinating and often tumultuous world of earthquakes. We've seen how the Earth's tectonic plates are constantly in motion, engaged in a delicate dance of collisions, separations, and sideways shuffles. These movements shape our planet's majestic mountains and vast ocean basins, but they can also unleash tremendous energy in the form of earthquakes. Fault lines mark the battlegrounds where tectonic plates meet and clash. We've delved into the science of seismic waves, those ripples of energy that radiate outward from an earthquake's origin, carrying vital information about the Earth's structure and the forces at play. From the speedy P waves to the ground-shaking S waves and the rolling thunder of surface waves, we've gained a deeper appreciation for the intricate ways in which earthquakes make their presence known. But beyond the scientific marvels, we must remember that earthquakes are a powerful reminder of the forces of nature that shape our planet and our lives. While we may not yet be able to predict earthquakes with pinpoint accuracy, our growing understanding of these phenomena, coupled with advancements in early warning systems and earthquake-resistant infrastructure, empowers us to be better prepared for the unexpected. Just as we rely on weather forecasts to guide our daily decisions, we can use earthquake hazard maps and safety guidelines to make informed choices about where we live, work, and build our communities. Remember, science is an ongoing journey of discovery, and the quest to unravel the mysteries of earthquakes continues. By supporting scientific research, promoting earthquake awareness, and fostering a culture of preparedness, we can collectively work towards mitigating the risks and building more resilient communities in earthquake-prone regions. Every earthquake, while potentially destructive, also presents an opportunity to learn, adapt, and strengthen our resolve to live in harmony with our dynamic planet. As we look towards the future, the dream of accurate earthquake prediction may still be on the horizon, but advancements in sensor technology, data analysis, and computational modeling are pushing the boundaries of our understanding. Imagine a world where cities withstand seismic events, early warning systems ensure safe evacuations, and communities recover quickly. This vision is within reach, driven by scientific inquiry, technological innovation, and a commitment to safeguarding our planet. As we reflect on the journey through the mysteries of earthquakes, we are reminded of the power of human ingenuity and resilience. The road ahead is paved with challenges, but also with the promise of breakthroughs. From harnessing cutting-edge technology to fostering global cooperation, our collective efforts can build a more resilient world. Imagine a future where the tremors of the earth are met with preparedness, where communities stand strong, and where the lessons of the past guide us towards a safer tomorrow.
Thank you so much for watching. We really appreciate it. If you enjoyed the video, please like, share, and subscribe. And oh, don't forget to hit the bell icon to stay updated on our latest content. See you next time.